Welcome back. Today we'll be looking at Chapter 3, the importance of state functions. I'm a little bit less, it's more mathematical and less practical, but the math is still very important and how we look at this. So still worthwhile going through, even though it's not as directly applicable as, say, ideal gas law or heat and thermodynamics. So last chapter we looked at state functions of U and H and how they relate with our state variables temperature, volume, and pressure. And we largely just looked at them. Now we're going to go in and try to do the mathematical functions to prove them and try to really attack them internally. So you do our thinking caps, so it's do this. But the first thing we need to do is understand a partial derivative. So a partial derivative is say we have a function that has more than one variable, like pressure. Pressure is a function of volume and temperature. Because R is the same. I mean, R is constant and essentially not going to change unless you have a chemical reaction. So we could derivate pressure with respect to volume and with respect to temperature independent of each other. So when we take the full differential of P, we can separate it into its partial differentials with respect to volume and respect to temperature. So we're doing the partial differential of, say, we're going to see this dP dV at a, so that's saying the change in pressure, how does that affected by the change in volume at a constant temperature with respect to volume, and dP dt, so the change, how does the pressure change with the change in temperature at a constant volume with respect to temperature. So knowing that the pressure is equal to RT over V, we do the partial differential with respect to volume. The derivative of 1 over x is negative 1 over x squared, because it's the x, it's the, you bring down the derivative is going to be n x to the n minus 1. So this is x of negative 1 to the power of negative 1, so you bring the negative 1 out front, and negative 1 minus 1 is negative 2. So that's where we get RT over negative RT over V squared. RT over V with respect to t, the derivative of x to the first goes to x to the 0th, thus the t drops out. And so the partial differential pressure with respect to each variable gives you negative RT over V squared dV and R over V dt. Now integrating both parts over an isochoric and isothermal change would give us how the pressure would change in this situation. So isothermal, temperature stays constant. Isochoric, volume stays constant. This leaves us the idea of a state function. So a state function, remember, is path independent. So we're differentiating a function with respect to both variables will give us the same result regardless of which order they're done in. So if I do dP dV and then d over dt, so if I differentiate it with respect to volume and then with respect to temperature, it should give me the same value as if I do it with respect to temperature and then with respect to volume. So let's look at that. So we said R T over V. If I do this d over dv first. That would give us that negative RT over v squared. And then if I take that whole thing over dt, the dt drops out, the t drops out, so you have negative r v squared. The other way, d over dt, rt over v drops out, t drops out, and you have r over v. And then we partially differentiate d over dv. B, still there, goes to negative r over v squared. The ideal gas equation is a state function. It doesn't matter which order I differentiate those state variables. I will get the same result. That's the idea of what it means to be a state function. And that will work for every state function, where let's see, we will always get an exact differential, which when integrated truly only depends on the initial and the final state. Now, there's a couple other mathematical proofs that are going to be of some use. So let's keep that in mind. When I say dx over dy, I can also equally state that that is equal to 1 over dy over dx. So, just like you should say, 3 over 5 is equal to 1 over 5/3. And the other thing is the cyclic rule. The idea that if I take the partial differentials with respect to each variable in turn and multiply them all together, I will get -1. So dx over dy, dy over dc, dz over dx. Now you'd think that each one would in turn cancel each other out, and you'd have +1, but we actually get -1. We'll see a proof. So dp over dt, dt over dv, dv over dp. So we're going to use this to solve some partial differentials. Let's see the proof. So it doesn't really matter which one I do. I can do dp over dt. So we said p is rt over v, dp over dt. So dp over dt, that's going to give us r over v. That's dp dt. Now dt over dv. So t is going to be pv over r. So that's going to give us p. It's going to give us p over r. And then finally, dv over dp. Come around again. And that's going to be rt over p. Okay. So this is going to be the same kind of thing we set up with. That's going to be negative RT over P squared. So what we have, we do that, R over V times P over R, those cancel out, times negative RT over P times P. So those P's cancel out. So you're left with negative RT over PV, which on itself, that's not equal to -1, or is it? Because PV equals nRT. So if you divide both sides by PV, you get 1 is equal to RT over PV. So that whole thing cancels out to give us 1. So we have -1 is the solution to that cyclic function. So we'll use that cyclic proof when it comes down to it. Now, there are some constants for changing volume that we'll deal with. These are constants often used for on cases where the ideal gas equation will not come into effect. These are constants that maybe deal with solids, constants that deal with liquids, things we have to deal with that when we compress things that don't quite follow the easy equation rules. So we can calculate a compound-based constant for how volume will change with pressure, which is going to be our kappa, and how volume will change with temperature, which is our beta. These things will come into effect when we calculate a thermometer, because a thermometer will expand, the liquid will expand based on temperature. The volume will expand and go up. And how, if the pressure is reduced in a tube, how the volume will go up. So we'll now see the volumetric thermal expansion coefficient and the isothermal compressibility. At a constant temperature, how can compressing this change the volume? The matter shrinks from temperature. Now, we'll show the proof in just a minute, but we're going to define them as beta, which is our volumetric thermal expansion coefficient, is how does volume change with temperature at a constant P over the 1 over volume. So the beta is a constant for how does volume change with temperature. Well, you need what it's a volume dependent intrinsic property. So the more volume you have, essentially, the greater the change can be. And kappa is also a volume dependent thing. But that's also because as pressure goes up, volume goes down, it's going to be a negative 1 over V dV dP. That's how we're going to define those as these constants. We can either have an actual number or we can use that equation. So actual number or a way to calculate that with integral. So these new substances are this substance dependent constant allow us to solve for partial differentials of pressure in terms of only of the constants, volume, and temperature. So we're going to solve that dP in terms of beta and kappa. So we're going to get this and eventually get it to this. We're going to show, but how do we get that? That's a lot of magic mumbo jumbo. So the first thing we need to remember is our definition of beta and kappa. Oh, by the way, there's a lot of proofs in this chapter. Oh my. Beta is 1 over V dV dt. And kappa is negative 1 over V dV dP at a constant. Okay. So, remember, we said dP equal to dP dV dV and plus dP dt dt. Okay, so the first thing we're going to deal with is dP dV. Well, as we said, 1 over x can be equal to 1 over x over 1. So kappa, we can say negative the dv dp is equal to negative kappa v. But that is opposite from that. That's dp dv. So we can say dp dv1, that's equal to that. So I'm going to flip that to the other side and get that to the other side. So we have dp dv, is equal to negative 1 over kappa volume. And that goes in for here. Volume dv. Or negative 1 over kappa volume. Sorry. Now, here's where we need the cyclic rule for the next one. We have dp dt, but neither of these beta or kappas have dp dt, I mean both p and t in the same equation. So here's where we get the cyclic rule. Remember that we said dp dt times dt dv times dv dp. Okay, equals negative 1. Well, if I get these two to the other side, I have dp dt. So if I get those to the other side, I got dp dt equals negative dv dt and times a dp dv. Well, conveniently, we just found dp dv. That guy is negative 1 over kappa volume, and dv dt, we can, if we multiply both sides by volume, you get beta volume to dv dt. That's times a negative beta volume. So beta, the volumes cancel out, the negative signs cancel out. And so this whole thing goes to beta over kappa. If we actually have the numbers, beta over kappa, you plug those in. So, in mind, and when we integrate that with respect to volume, you get natural log of V. And when you integrate that with respect to temperature, you just get delta T. So, looking back, the problem. Let's compare the accuracy of ethanol versus mercury thermometers. The liquid is both allowed to expand in an isobaric fashion. How would the volume change compare for 1 mil of liquid over 1 degree temperature change? So if I want to compare, keep the pressure the same, the pressure the same over 1, we'll just say, so delta P is 0. And we want to say the volume will change. So beta over kappa for times delta T for the ethanol. But beta over, you can set this up as beta over kappa delta T equals 1 over kappa ln dF over di. So really the kappas cancel out. So it's really just the beta. In this case, 11.2 times 10 to the negative fourth times 1. And now, of course, it depends on what your volume is. So if you have 1 mil and you're looking at this going 1 degree, you have 1 mil goes to 1.001. If you have, say, 50 mils and you by 1 degree, you've changed by 50.05. So the error and the change, how much has changed? If you expect this to be linear, 1, 1, 2. We have essentially a 0.11% change. Now let's look at mercury. Once again, if the kappas cancel out, 18.1 times 10 to the negative fourth. Inverse log that. That's changed by 0.10018. So instead of 0.11% change, it's 0.18% change, meaning that over the same temperature change, mercury has a larger volume change, meaning it's easier to get more accurate markings. It's going to expand greater. So it allows a little bit greater of expansion. Now, we did that partial differentials of pressure, the ideal gas equation. We can do the same with internal energy, looking how that changes as a function of volume and temperature, and then look at enthalpy and how that changes as a function of pressure and temperature. So both are functions of temperature, but in some of these, they have different secondary variables. So starting with U, we're looking at the same thing. We break it down, du dt times at a constant v dt, du dv at a constant t dv, which it should break down to essentially the Q plus W, essentially. Heat, the change in heat, minus P external dV. Now let's look at each part independently, assuming a constant volume or temperature. So if we assume a constant volume, the equation will simplify to QV is being our du dt, which essentially simplifies that. Say if we take the dt out, QV dt equals du dt. Well, differential of heat is not an exact differential. Differential of QV can be an exact differential because we've specifically defined the path, and thus it should be constant. While the change in internal energy with the change in temperature is an abstract constant, is an abstract like differential, we can measure this, and that's where we get our C sub V. So whenever we see du dt, that's equal to C sub V. And we'll do that exchange very, very often. We're more often going to use the C sub V sub M, the molar version, but C sub V sub M actually will vary with temperature as energy is used to activate. So, but essentially constant when used over a very limited range. So it's going to be a little hard. We want to use this as a constant, but it's not always constant. But what this will allow us to do is we can calculate du sub v, which is simply n times the integral of t2 to t1, t1 to t2, c sub v dt. We've done that before. Now, determining du of a constant t is a little bit more difficult. We need to evaluate the internal pressure in terms of joules per meter cubed. Now, we will use this as an exchange of du dv, that temperature times dp dt over constant v minus pressure. Now, we will derive this a little bit later, but we need to discuss entropy first before we get to there. Just note, if we evaluate this for an ideal gas, you'll notice something very interesting. Well, interesting enough for physical chemists. Remember, dp dt, dp is so RT over V. dPdt becomes R over V. You multiply by T, so you get back to RT over V minus pressure. Well, doesn't P equals RT over V? If I subtract P from both sides, I get 0. And that whole term becomes 0 for an ideal gas, meaning that there can be no internal energy change from a change in volume for an ideal gas, because there is no gas-to-gas interactions. So getting gases closer together will not store up energy, nor will it lose energy. But if you use the van der Waals equation of state, it is not going to be the case. So you can store potential energy by moving a gas closer together. But essentially, what we get is the partial differential of u with respect to each variable is cv dt and tdp dt minus p dv. And that is the full partial differential of u. Now, James Joule set out to solve du dv experimentally through the following experiment. He took two flasks, separated them by a stopcock. One flask contained a gas, the other contained vacuum. The two flasks were placed in a temperature monitored water bath, and we say essentially that our partial differential with temperature for internal energy is going to equal to heat flow minus P dV. So setting up the systems in the flask, there is no external pressure in a vacuum. So the work done on the right hand of that equation will be 0. So the heat flow that we can measure should equal the heat capacity of the gas plus that work function. So he would measure the expansion of the gas and measure how the heat flow the water bath to the flask, and that happened. But seeing that the change in temperature appeared to be 0 for this equation, he erroneously concluded that the internal energy of this must have, for the internal energy change with respect to volume, must also be 0 for gas. Now, this would later be corrected by a mistake, correct this mistake with a far more accurate experiment in collaboration with Lord Kelvin. But the idea here is the change is so microscopic in most gases that the temperature change of our water bath, it was essentially not measurable. This is the idea of like, just because you cannot record the value doesn't mean there isn't a value there. It just means your accuracy is not high enough to handle them. Now we can do the same thing with enthalpy. We can do the partial differentials with respect to enthalpy. Remember, enthalpy is U plus PV. And if U can be dQp, P minus PdV, and H is QP, we can get some interesting things. We're going to DH is DH dt, dt, DH dP, dP. Much like with U, at a constant pressure, DH dt simplifies down to C sub P. We can find delta H at a constant pressure with no problem. But we will, how do we get the other part? We're going to have the other part is going to be DH, DU, DP, and then we get the partial proof with respect to the other parts. Okay. And that all right. I'm just seeing, I'm looking. So essentially we say DH equals DU plus DPV. And this is then split apart into dP or VdP and PdV. Well, from there, U, it can be split apart into U can be split apart into actually, sorry. Yeah, U can be split apart into, I wasn't wrong. Du dt d dt and du dv dv. H can be split into dh dt dt and dh dp dp. Okay, so we have dh dt dt and dh dp dt dp on the left side. We have du dt dt and du over dv dv plus vdp and p plus pdv on the right side. So quickly exchanging what we know and what we don't know. I'm going to save ourselves some time. We're going to say, because we're looking specifically for this over a change in pressure at constant temperature, all ones with temperature terms will drop out. So this whole thing drops out. Rewrite this. And we know the solution for dV. Rewrite this. dH dP we want to find this, is equal to, remember, du dv was t dp dv minus p dv. Now, factoring the dv in, we get negative p dv, which cancels out with the positive p dv, and t dp dv dv. Okay. Now, if we almost there. Now, if we divide both sides by dp, we get, that cancels out with that, and we get dh, almost done, dh dp equals t dp dv dv dp. I wrote something down wrong. Okay. Jeez. Okay, that's dt. Good Lord. Sorry, that's dptt. That's why. dv dp plus v. That's still a hot mess, which is we're taking one final step. That, and this is why that t matters. Why the t just fucked me, or at least tried to fuck me, because that is part of the cyclic rule. Remember, we have two p's, and so we can exchange that for the next part of that cyclic rule would be dv dt or dt dv. Get it to the other side, that is exchangeable for negative dv dt. So our dh dp is equal to negative t dv dt pressure plus v. That is our exchange for dhdp. Once again, it is ugly. It's very ugly, much like our du dv. But once again, for an ideal gas, that will just drop out and leave us zero for the exact same reason. But, okay. So looking at CP and CV once again. Another thing we'll deal with is looking at the relations of C sub P and C sub V in terms of beta and kappa for a substance. And so how will we do this? So this is the proof we're going to get to. So how do we go about this? The first step is we start from our statement of enthalpy. Then dH equals du plus pdv. Now, and it'll also equal vdp. Remember, we said that delta p equals beta over kappa delta t and negative 1 over kappa ln v. So we're going to set this artificially at constant pressure, so this term drops out. And of course, that means our VDP will drop out. At constant pressure, this, which is a function of T and P, will just be C sub P dt, because that part's 0. U, which is a function of temperature and volume, will not. That will be C sub V dt. And we have this being du dv p, all that with respect to changing volume. Well, if I divide both sides by delta T, we get C sub P equals C sub V plus du dv. This is why I pulled this into there. Parentheses, dv over dt. Now dv over dt, okay, so now I'm going to do the exchange here. So this was equal to T dp dt minus P. So minus P and plus P cancel out, so that whole term drops out. So I have T dp dt d times dv dt. Over here. By itself, that's kind of ugly. But we have dp dt. dp dt was our beta volume. So we have C sub P equals C sub V plus beta volume and dv dt. Don't, oh, sorry, T times beta volume, sorry. And we don't have V sub T. But, oh shoot. The dv dt is our beta volume. That's our beta volume. So dp dt, we don't have that one. We don't have that one, but we don't have that one, but we can get it. So because of the cyclic rule. The cyclic rule says dB dt can equal T dt dV dV P1. So dP dV would be dV dt negative dV dt dP dV. Those are going to go in there. And once again, dV dt is our beta volume. So negative beta volume. And dV dt, dV dP is, this whole thing is equal to 1 over dV dP, which is kappa volume. So that's going to be equal 1 over negative kappa volume. So negatives cancel out, the volumes cancel out. So basically what we have is C sub P equals C sub V plus T beta squared volume over kappa. So this will allow us to directly compare C sub V or C sub P for real substances that aren't ideal gases. That C sub P thing only holds true for an ideal gas that follows that set comparison. Other things, the volumetric expansion and isobaric expansion, is not the heat capacity at a constant volume and heat capacity at constant pressure are not always the same by 8.314 because they are real substances. So looking at the temperature change, the molar volume, if we know our beta and our kappas. Comes back to our Joule-Thomson experiment. So in this experiment, they tried to measure du dv again. And we'll understand why a nitrogen tank will get colder when N2 is released. If you release N2 out of a liquid nitrogen tank, the tank you'll see ice condensing on the surface of that tank. But if you do the same thing if you have gaseous hydrogen and you let it release, the tank will actually heat up as the hydrogen is released. So there's an opposite effects as these gases are expanding outwards. So what they took is a thermally insulated pipe that's separated by two pistons and an adiabatic but porous plug. So this plug up here will not allow heat to flow through, but it will allow gases to flow through. It's going to insulate both systems without, so the hot gas on one side cannot make hot gas on the other. So essentially, as the pressure, the pressure on two sides of the pipe are constant yet different. So the pressure on the left is maybe high, the pressure on the right is low. So, but they're kept constant. So neither change through this whole process. So gas is forced through a plug in an isobaric fashion. So the left piston into low pressure region, the pipe, while the right piston moves with the expanded gas, allowing the gas pressure to remain constant on both sides. So as this pushes it through, it's keeping the pressure constant and high as the gas trickulates to the other side, and the pressure is kept really low by this, allowing this piston to expand a lot. Now, depending on the gas, it finds that as it expands on the right side, the gas will either heat up or cool down based on what we call the Joule-Thomson coefficient, or mu JT. And so this idea here, the same idea that used for air conditioners and refrigerators, that as we allow compressed air to expand, a lot of the airs will cool down as they expand. And this cool air can then absorb heat from a system. And thus we move the air out and then recompress it, and thus we absorb a bunch of heat from a region. So one last proof, and maybe a problem, maybe. Not too likely. I know this is a lot of proofs, but after this we're done. So the idea here is that we're looking at the total work here. The work done on the left is equal to plus the work done on the right, the total work done in this system. So on the left side, the work on the left is equal to, at the P1 equal to the integral of V1 of 0, because it's going to essentially compress this until the volume is 0. And on the right side, you have P2, and we start at 0 volume and going to V2, some different volume, dV. So essentially you get this as negative P2 V2 plus P1 V1. Now, because this is adiabatic, the heat is 0. So delta U, so this whole thing is our delta U. The internal energy of this system is equal to delta U. where break that down into U of the second situation minus U of the first situation. Now, getting the 2's to one side and the 1's to one side, so you got U2 plus P2 V2 equals U1 plus P1 V1. What you get, this looks like U plus PV, that's H. That's H at the second situation, and that's H at the first situation. So what does this mean? Under this specific situation, this is isoenthalpic. So over this whole crazy Joule-Thomson experiment, the whole system is not allowing enthalpy to change at all. So we have essentially that E sub T. How does temperature change at pressure with a constant enthalpy? Expansion of gas is equal to our mu JT, our Joule-Thomson coefficient. Our mu JT. So if we have our dH, which is equal to dH dt plus dt plus dH dP, and that's equal to and when we set that this is isoenthalpic, so that dH is equal to 0. We can say that 0 equals C sub P dt plus dH dP dP and divide both sides by dP. Divide both sides by dP. What we get is dt C sub P dt dP, which is mu JT, equals plus dH dP. Getting that to the other side, we find out another way to solve for dH dP for a real substance that's equal to negative C sub P, which is pretty easy to find, and mu JT, which is a substance-dependent constant. So meaning you can multiply that and look at how enthalpy will change under changing pressure for ideal constant, or ideal for a real substance. Okay. Once again, for an ideal gas, mu JT is 0. But oftentimes we do not have ideal gas because gases can liquefy. Ideal gases cannot liquefy. So if a gas is compressed to a high pressure, allow it to expand through a choke point. So a choke point, so it's like a little narrow inlet, expands out of there. It's going to cool. Most of this is going to condense. But the cool gas that isn't condensed is going to further chill the hot gas, and it's going to go through the system again. It's going to go through here, compress, get chilled by the gas that's expanding to the point, get to the point where it's almost liquefied, expands more, going to condense, and you can keep sucking the air out by doing that. You can liquefy the air, so you can keep processing that. Now, and that's essentially this chapter. I know there wasn't I didn't do any math problems. I'll maybe show some math problems later, but right now, the idea, I'll say quick thing, let's see. So you can try some And in order to really understand this, you have to try some problems, and I'll try to show those later. Well, have a good day. Like and subscribe, yada yada.